type something in the chat if I'm coming through. Maybe, hopefully. Yep. Okay. Thank you. All right, we're gonna go ahead and get started. Thank you for coming today. My name is Dylan Agnes. I'm with the Integrated Design Lab, University of Idaho. I'm a research scientist. The IDL focuses on education, outreach, and technical support for high performance buildings in the Intermountain West. We're currently about 7 to 8 strong, depending on projects. Always looking for additional students as we take on more work. So if you know of any students interested in high performance building design, let us know. And I hope that did not come out right. So this lecture today is sponsored by the Idaho Power Company. We have several other programs that they sponsor as well that we run. One of them being the Energy Resource Library, or ERL. It's a collection of over 900 building diagnostic tools. So anything that pretty much deals with electricity in a building, we have a tool to monitor or diagnose the performance of it. It's a free resource. If you're an Idaho Power customer, you just go online, create an account, that's free. We collect some information more like, hey, what's the building size? What's the building type? What are you measuring? You know, fan, pump speed, etc. We also have some things that don't deal directly with electricity, such as light meters or air quality meters. So yeah, please take advantage of that resource. Just yesterday, I checked out a sound meter to Hummel Architects. They're looking at some acoustic problems they're having in one of the lobbies of the building they just built. So yeah, it's very helpful. Another one is BSUG, Building Simulations Users Group. This is where we meet 6 times a year. We're changing up the schedule this year. I'm not in charge of it. We've handed it off to someone else. So look for that on our website. We'll be posting updates about that. But deals with, you know, AutoCAD, Insights, Revit, Energy Plus, Open Studio, Safaria, just looking at different standards, workflows, methodologies, if you're interested in building performance simulation. Another one we have is our luminous level lighting controls. We offer a training and a lunch up in our office. We currently have 27 of these LLC lights installed in our office as a showcase demo. So I give you a lecture on the technology, and then the second half of it, we go through and play with the lights essentially. I show you the user interface, how easy it is, the flexible control strategies you can implement, and things like that. That one's not an hour, that one's 2 hours, just FYI, but you can request one for your firm. Next, we have technical design assistance. This is broken out into 3 phases based off scope of work, where we provide varying levels of energy efficiency and technical assistance and project-based training. Phase 1 is anything less than $2,000, and that could be you're working on ASHRAE 90.1 or IECC 2018, and you have a question about code compliance. Or maybe you're thinking about, you know, what's the best option for me? Is it the constrictive or is it the prescriptive performance path? And so we can help you through that. As well as maybe, you know, you're getting an error in a software simulation program that you're running and you don't know what it means. You can call me up or send me an email and I'll look into it and get back to you on that one. Phase 2 is $2,000 to $4,000. It's basic simulation analysis, project review, walkthrough, recommendations, things of that nature. Anything over $4,000 gets rolled into a phase 3. The reason why it's a phase 3 is because that has a cost share agreement. So 25% is covered by the owner and 75% is covered by the Idaho Power Company. That scope of work has to be approved before we begin work. But we generally have a 1 to 2 day lead time for that, getting it turned around. So please take advantage of those. And then Jonathan is here from Idaho Power. You can talk to you about the commercial and industrial energy efficiency program. Do you want to say anything?
I mean, nothing. But I mean, because am I good from back here?
Yeah, I think so.
Okay. We have Jonathan Gwines, Idaho Power. So I help manage some of our energy efficiency programs. We're super happy to work with IDL on all this and trying to educate our customers on some of the measures that we have. We do have quite a variety of programs that help our customers to enact energy efficiency at their site. We actually will pay incentive for customers that are under code for pretty much anything that runs electric. So if you have any questions, by all means, come to me. I can get you pointed in the right direction afterwards or at any point. So, thank you.
Okay. There is a professional incentive program, so keep that in mind. And so that's if you as the architect or engineer are walking your client through the Idaho Power incentive program, you're filling applications on their behalf. You'll get paid up to 20% of their incentive, up to $5,000. That goes directly to you, not to the owner, and then to you. It's directly to you, and it doesn't come out of the client's incentive. Okay, so just kind of a way to kind of get you guys to learn the incentive program. But the reason we're here today, let's talk about the architect's business case for energy modeling. So why should you care and what's in it for you? So real quick, business case versus business plan. Business case being an examination of a potential market opportunity at the product level. Business plan, essentially taking that and scaling it up and figuring out how we're going to incorporate it into our business, step by step, every project or every project of type A. So an example of that would be introducing simple box modeling or early daylight analysis into the design process for every project, expanding the firm's skill, services to add economic value to your business or clients. One of the ways you can do that is, LEED compliance, going above and beyond code, standard, other awards, things like that. Business plan would be offering the services full-time, investing in, a handful of software programs. As well as diagnostic building tools for post-occupancy evaluation. We want to validate our design decisions and the calibration that happens on a building, every 6 months to a year after it's been operating. So, and AIA actually has a publication on this. It's called the Architect's Guide to Implementing Energy Modeling in the Design Process. It's first published in 2012, was updated in 2019. If anything, that should tell you how much they actually care about integrating energy modeling into the design process. So if this continues at this rate, we'll see an update to it in 2 years. But a lot of it kind of goes against the grain of what ASHRAE, that's the engineering side of energy modeling, or the AIA equivalent for engineers. And they have a lot of good resources, helpful tools, software, application workthroughs, things like that already done. And AIA is basically recreating the wheel rather than just adapting and changing what ASHRAE's already done. So we're a little behind the curve. And some of the terminology they use in that book is not applicable to what's considered market standard. But energy modeling in its simplest form is a calculation engine that accepts inputs such as building geometry or characteristics. And then these inputs are processed by the engine to derive output such as performance comparisons or reports for analysis. So the simple one is you have an occupancy schedule, your lighting power density, put those into the engine. The result is going to be your lighting kilowatt hours. Okay. The energy modeling, as well as focusing on energy efficiency, is not meant to overcome, adapt, or replace the importance of design. Okay. It's meant to be used as a tool throughout the design process. It can test various forms of design options, kind of like to think of it as like a what if. What if we did this equipment instead? What if we did this window to wall ratio? What if we did triple pane instead of double pane, or triple pane versus double pane low E coating? Looking at those options and exploring how vital they are. Like I said, it can use throughout the design process. So pre-design, design, and post-occupancy. Each of these kind of has its own wheelhouse on how you should approach it. Pre-design, we're making educated guesses. Okay, that's perfectly fine. Post-occupancy, the value is known, and now we're measuring that against our baseline of design and seeing how far out of our margin of error, so to speak, is for calibration. Like the building should be using this much energy, but it's using this much. And you have the same problem if it's using less energy, because then we over-design, we overpay. So finding out the balance for that, and design is kind of in the middle of those two. So for energy modeling, you don't need to become a technical expert, okay? A working understanding of the process or the workflow is more than enough to kind of empower you to utilize this for your business. And so what do I mean by that? I mean, there's going to be certain checkpoints in a design process where you have to stop and collect information. So like, what is your U value? What are your R value? What are your material specifications? How's your, building form, your building shape, orientation? Stopping and documenting those, handing those off to the proper people, whether it's inside your firm or a third party, and giving you those makes that a seamless transition so the energy modeling process can begin while you're still doing the design process. So the design language foundation is based on what if, but as we go through the design process, what if starts to be replaced with does this meet standard? Okay. And so the standardized design process in engineering would begin with analysis and simulation if necessary. However, it follows a very similar process to design. So if that's true, then you can insert it and go back and forth between the two at any point for either process. So basically design, energy, economic incentive, going back and forth between those. And so economic incentive is very important. Unfortunately, I see it tend to be introduced towards the end of the process, like, hey, here's what we have, let's see what we can get, versus looking at the incentives at the beginning and trying to see if those can inform your design decision so you don't have headaches down the road. And as soon as a variable has a value associated with it, so that means like our LPD, right? We have our LPD and our occupancy schedule. We can then use the engine to get those to kilowatt hours. We can translate kilowatt hours into money by saying how much it costs to operate that lighting system. Okay, so now we have an inherent value associated with it. And because of that, we can apply the incentive and we can see if it's coming out positive or negative for our rate of return. And that's very important because that is the language most clients speak. Okay, so being able to translate energy into the economic impact makes it viable for them to hold it, to understand it, to measure it in their world. Okay, so it makes the conversation a lot easier. One of the things, so like if you go to your client and say, hey, the building's using an EUI of 50, I have no idea what that means. Like EUI is also misleading because that's not the actual unit, it's kBTU. So again, context matters, the language you're speaking in matters, and being able to translate for your client so they can interpret the results and understand them is very important. But it's also important to us as well. So EUI 50, the context of that needs to be explained. So building size, climate, and building type are all used in that performance scale for it. So if we have an EUI of 50, but the average EUI for this size type building in the climate is 32, we're not doing so good. We're over 32. But if the average building in that climate size and type is 70 and ours is 50, then we're doing really good because we're 20 points under. Okay, so context is key. And so depending on, so here we have the EUI, and then in yellow, we have the average for it. And so context is key for determining its performance based. Now there is an inherent flaw with this metric because if everyone is a high performance building, then no one is a high performance building because that's the new normal. But so we're trying to get as close to the edge as possible without actually ever going to be able to touch it. So that's kind of the ultimate goal. And so, as I said earlier, going from design to kilowatt hours, i.e. energy, and converting that into dollars or economic incentive for payback and rate of return. And so what that really means is kind of into two processes. So here we have, this is our as design, if we didn't do energy modeling or simulation, but then we did a bunch of it and we found out, hey, if we chose this design path, these systems using these control strategies, this is theoretically what our load could be now. Okay, so that's our baseline savings. Now in the book, they kind of put these two together, but to me that they're separate. Okay, so this is your base load, your hardware, your equipment, right? This is your operating, right? Your systems, how optimized they are. So i.e. commissioning, right? So if we don't commission anything, this is going to be full. If you do commission, we're going to, save 10, 15%. If you have a good facility manager after 6, 9 months or a year, then, we've really optimized the system. He knows his setbacks, he knows his timings, he knows his loads, he knows the occupancy schedule. All of that has been now defined over time. And so now we arrive at this point. With energy modeling, we can do all of that and we can start here. Or if we're not starting here, we're starting right here, 10% above it. And so then we just have to capture that 10% over here versus making major changes and alterations to the building over a year. So saving that 10% over year versus going that 50% over year saves us energy, time, and investment. And so in the book, here's how they think architectural and engineering involvement should be done. This is true in a vacuum, right? We know that's not actually how the design process works. We're taught in school that it's very linear and straightforward. Occasionally there's a detour or roadblock, but in reality, it's a little more like organized chaos, right? We get there eventually. We know the checkpoints. We know we're going in that direction, and it's a little more loose, right? Sometimes you know things from previous projects. You have experience. You rely on that, so you don't need the engineering team right away. So it's trying to make the process more efficient over time. And so it's not linear is basically what I'm trying to say. And so here's kind of a translation for those, for like a design decision, your formal orientation that informs your solar geometry. So photovoltaics, renewable energy, or daylighting design, daylight harvesting, reducing our kilowatt hours. Roof form and slope, also the same thing, but now natural ventilation, or can it be solar ready? Structural systems, thermal mass, floor to height, daylight, also ventilation, wall design, thermal mass, insulation, heat transfer, window size, window to wall ratio, things like that. So these are the direct correlation of impact. So when you make this design decision, you're also making an energy performance design decision. Okay, so you have to be aware of the two and how they're linked. And so, and it's also like painting where you do layers, where one layer doesn't look so good, but once you add the second, third, and fourth layer, it all starts to come together. Same thing. One control strategy may save you 14% here, but then increase 5% elsewhere. And so you have to do another strategy to get rid of that 5%, but then your 14% goes to 8%. But the difference there is that we have a net positive of savings. So this is straight from the textbook they have. BPS can test applicability of rules of thumb for on a specific project and inform the development of future details to be applied in a given climate of project type with similar loads. The reason why I don't like this is BPS stands for Building Performance Simulation. No one says that. Say energy modeling or BIM, Building Energy Modeling. That's what the industry says. But if you see it in the text, that's what it's referring to. So you can, if you want to look up ASHRAE, you can find the equivalent of it. And simulation gives us a peek into the future through virtual environments that follow the rules of physics. Again, this is misleading. The rules of physics are whatever we decide it to be. Okay, so that's how accurate it is. And that comes from a data science theory called GIGO, garbage in, garbage out. So if you put bad data into your engine, no matter what you do, you're going to get bad results. So data integrity is key. And so being able to control the virtual environment and mimic it as real as possible, you determine the rules and you have to be aware of that because you have bias. You can offset those and it can have impact on your analysis. The second part of it allows us to test assumptions and optimize solution for better outcome is right on the nose. That's exactly what it's for and what we're using it for in our industry and in many other industries. And so I like to refer to that as data-driven design. So as I mentioned earlier, you guys rely on experience project to project as you go forward. And so all firms, designers, engineers do this in some level. So you can specialize in a certain building type, such as schools, office, or medical facilities. Once that school has been built and constructed and designed, you don't forget, the contract supply chain, the code requirements, egress, commissioning, everything like that. You remember that, you take that and you move it on to the next school project. And it makes it more faster or efficient. And hopefully we can get a better school design out of that because you're spending less time on those typical tasks. So we compound that and we add it, and that kind of gives us this process. So we have rules of thumb, right? Door should always be this far. Egress is like this. Elevator goes here. Water fixture plumbing goes here. Electrical closet is probably going to go here. Oh, it's a south facade. We want to take advantage of the sun. We're going to put the classrooms and everything there. Things like that. Enough rules of thumb get strung together, that becomes a workflow. Enough people use a workflow, it becomes a best practice. If enough people adopt the best practice, it becomes a code or standard because we want everyone to do it. Now, the way I describe that, it seems like we're just stepping up. A workflow, it can step back down too. So something can be a code or a standard, and then something else comes up and replaces it. Not that that's not relevant or whatever, but it's a best practice for that specific situation now. We have a new overall code standard that we want to follow or have everyone adhere to. So virtual prototyping is essentially what we're doing for our buildings. Most products, if not all in the 21st century, are tested in a virtual environment before being built physically. And even then, we still test them again in the environment because we actually have the real world now. So simulations can allow us to see into the future through virtual environments in which we can control the rules or physics of that environment. So more accurately, we're exploring what if we rotate the building, every 45 degrees or every 90 degrees or every 1 degree, we can do that. What if we did that and increased the window to wall ratio? What if we did that and we added shading to the south facade? What are those impacts on there? And the reason why you do it step by step is so we can isolate the performance impact of each design decision. And then we combine them and we see what is the net result of those. Is it good? Is it bad? So building simulation, again, is not meant to supplant the importance of the design process. You went to school, you got a degree, you got certified, you work in a firm, you are capable. You read code. Code is more of guideline, right? You figure out how to put the square block into the circle hole. Okay, so consider it as a tool in your tool chest, right? You don't use every single tool you have on the same project. You decide when it's applicable, when it would be best, right? You make that decision. Same thing, energy modeling is a tool in your tool chest, pull it out when you need it, okay? Don't rely on it for everything. So I'd like to pause here and ask for any questions. If there are no questions, I'm going to be addressing these questions in the second half of the presentation. Any questions?
It's important, the key comment you made, that a lot of the, nowadays, that a lot of the stuff that comes to market is designed in virtual reality. Like there's testing, there's aerodynamics, all that stuff is being tested. So why not consider that for our buildings as well? Like why we model them correctly in Revit or whatever program we're using, and also test them for these energy efficiencies. So that's for me, it's a selling point to be able to say, let's do this look at this.
Yeah, I go into that more. So online, any questions? No? Okay, feel free to type them in the chat or unmute yourself. Either way works for me. All right, so what can you model? So it's typically broken out into two phases: whole building simulation and single instances. For whole building, we're going to test all or as many as available to determine how elements of building design will perform under real world conditions. So this is typically what trips a lot of people up, is because like, well, I don't know all my variables. That's fine. We have default assumptions that are literally written in code, in standards, and best practice workflows. Use those. A lot of them are built into the software program now to be the default value. The thing that you have to remember is as you go through the design process and you find out those values, then you have to plug them in and rerun the simulation, because now we have more accurate details, and that's going to change as we go through the design process. And so the single instance, I like to think, is a subdomain of the whole aspect where we're just isolating one portion of the building. Typically, you're going to see thermal, lighting, acoustical, or airflow. One of the software programs that does one aspect of this really well is Insight from Autodesk. Their user interface for the analysis of the results is really good. They use widgets that are interactive. And so, I told you we could rotate our building every 45 degrees, right? So if we do that, that's 8 simulations, okay? Now, say we want to test 2 window to wall ratios for each of those, 16. Actually, not 16, 32. And so it just keeps growing and growing and growing. Autodesk says, hey, I don't care about that because I'm going to make you use our cloud computing service. And so we're going to run all those simulations. So there's a couple hundred simulations that get run when you do one building in the Insight. It gets uploaded to the cloud and it replaces each of those variables. What if your visual transmission was 30% versus 70? What if your R value was 10 or 14? And it considers all of those so that when you flip this widget around on here, you can select the value. And as you select that value, it's going to update your performance score. Okay. And it gives you the context. Like I said, context is key. So it'll give you the average for that building type. And then it'll give you the ASHRAE 90.1 standard that says, hey, if you want high performance, this is what we say is high performance. And then it'll keep track of it saying, hey, here's your baseline. Here's this widget switch that you made. And here's the impact. And you'll notice it's on a bar like this. And so this is a range. So it's saying you could use this much energy or you could use this much energy. That's the range of your current design. And as you go through and choose and try to optimize your building design, this range will get smaller and smaller and smaller. And so then you have a better idea of where you're going to hit the target, where you're going to land. Okay. And that's much better than having the huge range. So we narrow it down. Like, okay, so if we stay within these parameters, this is our sandbox. As long as our building is within these parameters, we're gonna be fine. So, and this interface is meant to bring the architect, the engineer, the construction manager, and the client all at the table at the same time early in the design process. So everyone's giving input, everyone knows, there's no surprises done. What do you mean we're doing this standard? Well, actually, we went over that. Now you know ahead of time. So for our industry, what we typically model, daylight simulation, energy simulation, and computational fluid dynamics. So what can you model? For daylight simulation, it's in two parts, qualitative and quantitative. Qualitative being subjective, it's luminance or glare. That's entirely dependent on the user. Example I like to use is me and my boss. My boss is okay with working with the sun on his face. I am okay working in a cave with no light. Okay, so it's very hard to get everyone happy when it comes to glare or that. The quantitative is illuminance. We measure that in 2 units, lux or foot candles. Foot candles being the US customary system, lux being the metric European system that everyone else in the world uses. Energy simulation, that gets broken down into 2 as well, environmental variables and then equipment variables. So environment being what is our humidity, what is our temperature range, heating and cooling degree days throughout the year, what comfort levels are we going to, equipment variables being whole building energy use, end use consumption, equipment parameters, control systems. So what's our setback? How early are we kicking our HVAC on? Are we doing any passive control strategies with mechanical control strategies? What are occupancy set points? What's our building occupancy? Are those things working as they should in a building that's been built? That's the importance of energy auditing or retro commissioning a building, is ensuring it's still operating as it should. Computational fluid dynamics, single point in time. This would be for more natural control strategies, so passive ventilation, looking at pressure, depending on the building type, what you're going to be using, airflow through an HVAC system. If it's complicated, you're coloring outside the lines. That's where energy modeling kind of gets useful. So who models? So sometimes it can be confusing, but we're talking about the one on the right. So there's 3 levels that are outlined, and I actually do agree with AIA in these. Level 1 is having an understanding, and this is what I recommend if you are an architect. So you have a modest understanding of the modeling process, the types of questions it can assist with exploring answers to. Typical, you'll get your variables together, you'll have an idea of what strategies you want to go to, and then you hand it off to a third party, and you start going back and forth from there. The downside to this is the turnaround or lag time. So it really needs to be thought out in the beginning. What are you going for? What software are you using? What are the limitations of that software? So there's no surprises down the road when you ask for something, you're like, hey, the software can't do that actually. We got to take it out. We got to remodel it in this one and run the simulation in that program. Okay, well, that just added 2 weeks to our project time. That's bad. So things like that. If you're looking to kind of get more, offering it as services full-time throughout the design process, you want level 2, exploration. You have some modeling skills in-house, so basically simple box modeling, nothing really complex. So think broad strokes. There's daylighting or energy concerns. This will let you run some basic simulations to kind of test, hey, is there enough useful daylight for me to use daylighting as the main lighting source for my building? And what control strategies can I optimize with that? And depending on the initial results, it could be, yeah, we should explore that, or no, there is not. Daylighting will be supplemental or accent at best. So I'll let you make that decision early. Ideally, it would integrate with an engineering team within the firm or an engineering firm that you work regularly with. And you tell them, hey, this is a service we want to start providing. What can you do to help us, have this be a continual process for our design? Level 3 is optimized, going off the deep end, full on, you're on board, someone like me. There's full-time energy analyst that is able to do HVAC analysis as well as architectural analysis. So notice I said HVAC analysis, not designing the HVAC system, just evaluating the performance of it and making suggestions or recommendations of what needs to happen to the HVAC system. Not necessarily that you understand what to do with that, but then you work with the engineer. Okay, so back and forth, integrated workflow. Okay. Full service firms can have a competitive edge in the market, and this has the fastest turnaround. Okay. especially if it's, integrated into your design process. Everyone in the firm knows it. Everyone at certain checkpoints is compiling the data they need, handing it off to someone, they're compiling it, and then it goes to the energy modeling team. Okay. So how can you use models? So like I said, BIM, building energy modeling, not to be confused with BIM, building information modeling. The two are heavily correlated though. But so it's kind of like a Swiss Army knife. It's kind of where you need it to be applied, it can be applied. And so code compliance, lead compliance, design assistance, measurement verifications, operations improvement, and incentive programs. So for code compliance, it can help you ensure code or standard compliance for your building, as well as if you're coloring outside the lines, which is okay with code, but it has to pass muster. Energy modeling does that for you. The other way is it can identify the context of the goal and the steps to reach the goal. Okay, we have identified that goal. Now, how achievable is it? How many steps, how much resources is it going to take to get there? Therefore, is it worth it? For lead compliance, I've gone through lead. Here's everything in lead that mentions or requires you to have some form of energy modeling of some type, form or another. So you'll get points for doing energy modeling. The easiest one is the integrative process, which means at the beginning of the project, you sit down with the engineering team and you work through some simple box modeling. Doesn't have to be good modeling, doesn't have to give you results. You still get the credit. It's because you sat down and you started the integrated process early. That's the important thing. Design assistance, again, assisting you all the way from, hey, we got a project, here's our Part T diagram, or here's our basic spatial analysis to, okay, let's get some, drawings out to bid, or, okay, now we're building the thing. How do we do that? So the design assistance areas would be massing, ventilation, daylight, energy program, and most importantly, all that accumulates to feasibility studies. How feasible is this design? Because remember, while we care about energy efficiency, occupant comfort is also important. Because if occupants override or are not comfortable with the current control strategy you have implemented for your building, they will override them, and more than likely or not, you'll be using more energy than you actually intended. I've seen that in way too many buildings. So conceptual design. So looking at different box modeling, orientations, different daylighting strategies, and seeing the impact that will have. So keeping all the hardware, the equipment, the mechanical systems the same, just looking at daylight and saying, okay, all these daylight designs work, which one's energy efficient? And so going through different versions and figuring that out. And you can do sub-ones, so we have V2A and V2B. So same design, but we just rotated and did a couple different control strategies to see the impact of it. Another thing you can do, it's important for presenting your analysis. I love looking at tables and basic charts and graphs. Your client probably doesn't, as do most architects. So being able to come up with different ways of presenting your analysis is also important to convey your ideas. So this one is energy programming for daylighting zones and demand. So this is, so the building, so we see buildings as architects as spaces. Engineers see them as thermal zones. So while you see 5 individual private offices or breakout conference rooms or whatever, an engineer sees one thermal zone, because those are all going to be heated and cooled the same, and their occupancy schedule is practically the same as well. So this is what that does. So it combines our individual spaces with their thermal zones, and then we're mapping it on, okay, here's what IES, the Illuminating Engineering Society, or our manufacturer, says we need for our space side: 20-foot candles, 30-foot candles, 40-foot candles. Based off of our simulations that we've done, here's the amount of foot candles available currently with our design. So now we can see how difficult it is, how much we have to invest in daylighting to get our levels up to performance, so we can get credit for them and receive a good rate of return for our payback. Okay, so like this space, the admin area, requires 50-foot candles. We're currently getting between 5 and 15, it looks like, somewhere in that range. Okay, so not really good. But for our bigger areas, like the gym area, low amount of foot candle requirements, fits in our range. Okay, we should invest in daylighting for this space, but not necessarily this one. Or depending on if, say, all these spaces are viable to be daylit, but we weren't planning on it and we were planning on doing these. Okay, now we need to go back and rethink our design and basically try to get the inverse to happen. So there's multiple ways of doing that. Another one is a diagram like this, where we basically show, how the passive control strategy is theoretically working. And then we show our results. So here's what it is with a night flush, stack flush, cross ventilation, high performance envelope heat gain. Okay, and showing the layers of it. Switching real quick. So some of that might get overwhelming. You might not have time to do it. We have design tools on our website. These are completely free to use for you. You can download them. There's a variety. I think we have, we're at 17 now. So they range from COVID impact modeling to infiltration equations and conversions, insulation value calculator, thermal energy savings tabulator or test, weather normalization. We have the CVEX tool. We have the daylight pattern design guide. So these are where we basically done this for you, and you think of this as a rule of thumb or a workflow that you can apply and try to turn it into a best practice for your firm. So iterative analysis. So here we're looking at the envelope, doing daylight, adding a view window, light shelves, roller shades, shed roof, baffles. What happens when we add cubicles? Interior partitions and furniture arrangement is actually quite important when you're using daylighting as your primary lighting source, as well as then changing the cubicle size. So you can see how we're layering these and we're seeing the effects and the impact each strategy has. And we're just trying to get to a net positive. So here, we present that with the floor plan, with Photoshop with the analysis results over it. And then we can actually go in and create a camera in our program and take a picture and see what the light conditions would actually be like. We can also show that in section and see how well is this wall being washed for light distribution, and then how does that translate to the floor illumination. So then, so like I said, here you're only seeing, I think 8. There's actually over 30 run. Okay, but then we only present the 8 because we filtered down where, okay, these meet the client's criteria and demand and the standard for design that we're going to. And then we go in and like, okay, which one do you like? Okay, I like that one. Okay, we're gonna go in and we're really gonna flush that design out and, apply our what ifs to it. And so that could be something like this, where we have our baseline performance, then we add shading, and then we add degree control with our overhang. So now we're blocking out the sun for a certain portion of the year and allowing it in for another. And then we add our high performance envelope. And so what does that mean? So here, 58.7, and then we end up with 46.7. But to get here, for adding our shading, reduce our cooling by 13%, but we increase our heating by 4%. But we've also decreased our ventilation, our fans, by 8% because we were blocking out the sun. Not specifically, we're just 3-foot standard overhang, right? Now we add the degree control to it. Okay, and so now we maximize our cooling, but we definitely are not helping our heating. Okay, so now we're going to add our high performance envelope. Okay, we lost some cooling, but now we're saving in our heating. Okay, and our ventilation, we're still having those same savings. And so now we have a net gain 20%. Okay, and we can break that down further, going into the comparison of the peak cooling charts and the peak heating charts and seeing where those savings are actually coming from and why. Okay, in this building, I know typically people think of lighting as LED now, but this was fluorescent. So keep in mind, those actually have significant contribution to the heating load, as well as the electricity load for when if you're going to do shading and degree control, then you're obviously going to want to do daylight harvesting, especially with fluorescence. So that's why we see a 62% jump here, but that's just not included for this one. So what if the data analysis, right? So gone over a lot, there's a lot of data there. And as I told you, this one was actually over 30 simulations, but we're only showing you the 8. How did we do that? Why did we do that? So unfortunately, there is such a thing as too much data, okay? Energy modeling simulations, the amount of parameters, the physics of what we're trying to create, which is the real world, or at least the environment that you're modeling in. There's a lot of data, okay? So that's probably the second thing that gets people bogged down is the first one being, what values or inputs do I have? Because I don't want to get a bad result. And the second one is, okay, I got the simulation working. What do I do with all this data? How do I process it? So now the market has kind of responded by creating software programs initially that were solely for data analysis. And now we've seen a lot of the energy modeling software programs adopt these and incorporate them into the programs themselves. So a lot of times now you don't have to export your data to perform analysis on it. You can do it right there in the software program. This one's called Design Explorer. It's Safari is one of them that uses this, and Project Stacio, that's the other one, sorry. So this is considering, you know, multiple different types of simulations, but let's walk through this and break it down. So we're going to follow the data, and remember GIGO, garbage in, garbage out. So garbage in, that's a fancy way of saying our input variables. Garbage out is a fancy way of saying our results. Now, so this line here, this is our floor or our minimum, right? We're not going to go below that. And this here is our ceiling and our maximum. We're not going to go above that. You'll notice each of these lines are different scales, okay? This one doesn't even start at 0, okay? Each one is dependent upon it. So think of it kind of like there's a minimum amount of window to wall ratio you're required to do for a space type that code says, right? For fire egress, sunlight, ventilation, etc., right? That's your floor, okay? Now the engineer is going to come at you and say, hey, we're doing ASHRAE 98.1. I'm doing this standard, so I'm using this section of the standard. Therefore, you're not allowed to have more than 35% window to wall ratio, or your visual transmission is not allowed to be above 45%, right? That would be our ceiling or our maximum. And so based off of data, so there's 5 variables here, right? But we're only testing 3 for our depth. And then for our window to wall ratio, there's 5 variables. We're only testing 3. Shading depth, 7 variables. We're only testing 3, right? But look how many results. Each of these threads out here, that's one simulation. How many results that gives us just for looking at a handful of variations. The real culprit for why we have an astronomical amount right now is the orientation, right? That's creating a lot of having our amount of simulations exponentially grow. And so basically what you need to be doing is applying your range, right? So I showed you that earlier on the Autodesk Insight. What that means is basically this is our range. Our cooling can't be lower than 1,000 and it can't be greater than 2,000, right? We've worked with our engineer and that's what they've told us. Here it's 3,500 to 5,000 kilowatt hour, right? We don't want to use more than 5,000. The base operating of the system, if it's not occupied, would be 3,500 or something like that. Our lighting, you talk to me, you're a lighting expert. And I tell you, based off the technology and the lighting power allowance for IECC 2018, you can't go above 400. For the basic lighting you have to install to meet programming requirements, you're going to be using at least 200 kilowatt hours, somewhere between. And you just basically go down the line and you do that. And for some of them, you can make theoretical. So like this is SDA, Spatial Daylight Autonomy. This is used for lead daylighting credits. And so here I drew, here's the 45 to 75 for 4.1, which is the requirements for getting credit. So you have to be at least above this line. And if you're above this line, you'll get credit, but you just won't get any more. You'll get, a nice pat on the back. Good job. That's about it. So, and you don't have to necessarily use, so you can do this earlier in the design process, not while you're in the middle of it. And so the way you do that is you rely on databases, which we have. So such as Energy Star Portfolio Manager. This one that I'm showing you is based on CBEX, Commercial Energy Building Consumption Survey. 2018 data was released last year. We've been working on processing it. So this is EUI by category and building type. And so this is looking at schools. So this would be considering all schools, elementary, high school, preschool, daycare, etc. And so we look at these and be like, okay, what is the average EUI for heating? Okay, now EUI kBTU, we can translate that into kilowatt hours. And so that's what you do. We have a design tool for that to help you. And so you would translate that and then you would say, okay, that's kind of like the average. Now we're going to reference ourselves. Are we above or below that average based off of this data set? Okay. Any questions on that? And this data information for CBEX on office, lodging, and retail, in addition to education, is available on our website for you to download. And so this is basically us just establishing a new floor and ceiling based off of the information we now know and performing analysis on it. And so we can kind of basically create our own new custom range. So now we say, okay, we want to, for our lighting, this is our range that we have to be in. Okay, but there's a bigger culprit based off of looking at that. And that would be our heating. So we really want to focus on our heating because we need that to be efficient based off of our initial estimates from simulations. And so we want to figure out all the simulations, all the threads that pass through this point, and this point, and this point, and this point, and eventually, if we're considering it, this point as well. And so then we're going to get rid of every other simulation. We don't care about those now, right? We have our floor, we have our ceiling that we know we have to operate in. And so now we're going to play in between these two lines, right? We'll run additional simulations. We'll look at design decisions, impact, etc. So the bands become the new overall floor and ceiling, which can be thought of as your design constraints, right? Energy code, building code, lead criteria, things like that. You're just making your own now, and it's kind of being compiled of all of those standards jumbled together. So design assistance, explore system types, iterate design details. So that's what I mean. So here we have our ideal baseline. Here's with an RTU, WRF, and just going down the line, testing different technologies, seeing the impacts, as well as then changing the operational parameters of those and trying to optimize them. And in a utopia, we arrive with a building like this, right? Use the least amount of energy possible while meeting all of its occupant comfort demands and criteria for the space types. So again, one of those ways you can do that is looking at databases that have compiled information on building system types. So again, we're sticking with education, CBEX here, 2018. And we're looking at CAV, constant air volume, versus DOAS, dedicated outdoor air systems. And so we come take a look here at high schools, see the heating is 53.09, and here it's 46.33. But again, context, so we got our sample size here, and we got the average square footage of that sample size. So 292,000 versus 215,000. Okay, so you can see this is a higher average square foot, and it's more efficient than this one. So it's actually, we're saving even more energy than we would if we're using a building of this size with this system type. Okay, so if we increase the average square footage to match this, this would significantly go up by at least probably 8 points or so. And so then plotting that and looking at across there, different ones, not just those two, but multiple systems and seeing which one works. And here it would jump out at you like, hold on a second. DOAS is great. I've heard a lot about that, but why is demand controlled ventilation performing much better than DOAS? And so we would look into that, go into that and figure out, okay, is DCV applicable to your building project right now? Or is DOAS better in the long run for maintenance, longevity of the system of the building? How long are you planning to operate it, et cetera? So, but this would basically tell us like, okay, we need to look at DCV and VAV and compare those because our client, you know, whether it's a school district or whatnot, is saying, hey, we've heard a lot about DOAS. We want a DOAS system. DOAS is great. You're like, okay, wait, hold on a second. Let me talk to you about these. And you can do the analysis and compare these two systems, present them to your client and show them this one is better energy performance wise, if that's the criteria you're analyzing. But again, not just energy efficiency. What is the longevity of the building? What's it being used for? How's it being maintained? Those kind of questions. And that's where measurement and verification comes into play. Energy retrofit process. So this is where a building has been built. We build an energy model as it was designed, and then we build a separate energy model, the exact same one, and then we're going to try to calibrate that by feeding in real world utility data, occupancy schedules, and things like that to calibrate and see, okay, what happened? What went wrong, so to speak, or what change caused you to use significantly less energy or significantly more energy? And verifying the performance also helps you with projects down the line because you have verifiable data to your clients. Because a lot of the times for energy efficiency measures, we're presenting them in a range because we don't know how someone's going to act that day of that year, right? If it's going to be fully optimized or not. And so by verifying the performance, you can go to your client and say, hey, this is the range, but here's our acceptance of this control strategies by building occupants, and here's how well it works. So case studies essentially for your client. So here's an example of that. We have the utility and electric use versus the modeled electric use for gas and electric. And so we're just basically trying to figure out, okay, so this is how much gas we modeled you to be using. The real use, okay, here's it's gray because it's less than what we modeled. All right, awesome. Wonder why that is. I'm just curious. So I'll go and investigate that, but it's a good problem to have. But then when we cross this threshold, it's like, okay, hold on a second. You're using more than you're supposed to. And so is this area greater or less than this area and the sum of this area? Because depending on that difference, if they don't cancel out, then you're using more energy than you intended. So sometimes that's good because, you know, building got calibrated, occupancy changed, something different happened, but it was adjusted and accounted for. So it's not necessarily a bad thing, but we just need to understand why. So to verify. Now, as far as what to model with, engineering, you're going to see eQuest, Radiance, Trace 700, HIP, Trans, Energy Plus, and Open Studio. Energy Plus, Open Studio being the most popular. Architectural, referring to daylighting. We got Honeybee and Ladybug, Radiance, AGI 32, Insight, Revit, and Light Stanza. The thing about the lighting one, Radiance is actually the engine and the software program. The problem with that is the software interface for Radiance is the command line. So it's non-existent. So typically what happens is you'll have other software programs, AGI 32, Light Stanza or Honeybee. They'll have the user interface, which basically means, hey, that's the pen tool, that's the pencil tool, that's the push tool. You know, there's a drop-down menu you can select from. There's options to export, things like that. But then in the background, Radiance is the engine that's being used for all of them, right? So if you think of Honeybee or Ladybug as the Mustang, Light Stanza as the Camaro, they have the same engine, just look different, okay? Depends on personal preference. It's basically what's happening. And then you have hybrids that can utilize both. Or real quick, Insight for Revit, they don't use Radiance. 99% of the daylight software simulations that we use Radiance. Okay? They decided not to. They have their own proprietary program. There are issues with it, but it does work. Okay, it has been verified. It's just different. They basically reinvented the wheel for no reason. Basically, is what they did. That's why we're really confused. And they were like, no one can look at our wheel. No one can know how it works. And we're like, it looks just like this wheel though. So, okay. So just keep that in mind. The energy side of it though does use Energy Plus. So again, Energy Plus is the engine. Open Studio is the car body of that engine. Okay, so same concept. So that's kind of why Insight's able to get away with it. They just change it for the daylighting for some reason. But if those don't work for you, there is a website. It's up at BIPSA, International Building Performance Simulation Association. They have what's called Best Building Energy Software Tools, and it's a directory of every single energy simulation software out there that you can think of. That's also a good thing as well as a bad thing. So use the filter on the left-hand side. So if you only want to look at daylighting, it'll show you all daylighting. If you only want to look at electric lighting, it'll only show you electric lighting. Just want to look at thermal bridging, only show you thermal bridging, as well as you can select multiple ones. Hey, I want to do energy and daylighting all in one. Show you all the software programs that'll let you do that as well. Okay. That's what I have for you today. Thank you for coming. Any questions? Oh, all right, let's give that to a different firm. They use ArchiCAD. Okay, online people, I launched a poll. If you could please fill that out for feedback. There should be evaluation sheets floating around. If you could please fill one out, I would appreciate that. All right, thank you for coming.
So for all the softwares that you talked about in modeling, I mean, for us, at the end of the day, we have to submit a contract to the building department. Is there, I guess, because initially we're gonna try to invest in the initial modeling, but then down the road, you know, might be the stamping architect or the jurisdiction's gonna say I need a contract.
So typically for that is you want software programs that are okay with exporting. And so what that means is, like with Revit, for their schedules are really good. You can create a, a schedule, whether it's lighting schedule, room schedule, etc. And you export that to CSV, and that would let you upload it into the contract. You might have to copy and paste and move some columns around, because it's one of those automated uploads where you basically submit your file and, like, the first row is, the outline of what each column is going to be. So the program knows, okay, these are the lighting types. This says it's LED, this says it's 35 watts. There are 30 of these, this is the space type. Okay, let me go pull from my directory. Space type says this is your lighting power density. Okay, number of lights, area, multiply it, boom. Okay, check it. Goes through all of that for you. Lighting column I don't know when they did it, but I was using it last year for some reason, and they did an overhaul of it, and it's really good right now. Particularly, I like to tell people to use it for figuring out your allowance. So code's pretty bad. It will tell you basically go shopping and then find out your allowance. And I think it should be the opposite. They should tell you how much lighting power allowance you have. Take that, then go shopping, and you can figure it out. The current com check that they have lets you do that really well. So you can basically figure out what your lighting allowance is, take that to your interior designer, electrical engineer, or I don't want to say lighting salesman because that's not what they're called, but like the latest, like the lighting representative guy. You go to him like, hey, these are the lighting types I need. Here's my allowance that I'm allowed to spend. Here's the building type, the space types. What do you got? And they should come back with you with, okay, all of these from our catalog will meet your demand. Which ones do you like? Okay, here's how many you need of each of them, and you're still staying under. And then you go to ComCheck, you input all that data in again to verify that you are under and in compliance. That's a very simple way of an energy model, right? We've isolated one thing, we've done it, we figured out, and we're projecting of it to kind of figure out the ideal path we need to take. We can stray from that a little bit. That would be our margin of error. Like we have, however many kilowatts you have to play with. Like, okay, our current setup, is like 95 kilowatts, but then you're like, okay, our limit is actually 110. So if we need to do some additional accent lighting based off the interior designer or the electrical engineer says, hey, emergency lighting has to go here. Okay, that's going to increase ours, things like that. So just working through all of that. Yeah. You're welcome. Thank you for coming. So Reed Weber, let me go to that slide. It was back in the very so one of the ways we offer assistance, Reed, is through technical design assistance. It's broken into 3 phases, depending on the amount of work. Phase 3 is important to note that if it's over $4,000, it's a cost share with 75% covered by Idaho Power, 25% covered by the owner. This ranges anywhere from I have a question about a software program or code or standard to, hey, we want to do energy modeling in our office, or hey, we really want to look at simple box modeling to incorporate into our process. We can work with you to do that. The last iteration I have for daylighting was I worked with Erstat Architects on how they can incorporate daylighting into their firm. They were utilizing Revit, Autodesk, so I was teaching them how to do insight daylighting analysis. So yeah, that was, I think, over 2 months. A couple lectures, a couple in-house workshops, a couple of you guys work, and then I will grade your work, so to speak. Yeah. I hope that answered your question. Anyway, thank you for coming. Hope you all have a lovely day, and if you're in Boise, the weather is nice, so you can get out to enjoy it.